Thanks for the, can you hear me? Yep. Thanks for the invitation, highly appreciated. Everybody's back from lunch, so you're in a perfect position to listen to a very long speech now. So I will speak quickly about the background of this project, and Anders will take the reality of it, the more technical part of how he really did it. So just a couple of words. So we are a market research agency. Ipsos, founded in 75, in 90 markets, 18,000 people, and we do quite a lot of research. So we do somewhere around 50 million interviews per year. And the background of this project was basically that we wanted to make sure that the questions we ask are more homogeneous, that we don't have a researcher in Malaysia asking the question in one way and a researcher in the US asking pretty much the same question but in another way. So we wanted to get more homogeneous in terms of the questions we ask. So the brief was basically, let's do a question library and let's get a lot of projects, and we took initially, so we do about 70,000 projects per year. So we have millions of projects that we have conducted, and we took a portion, we took 90,000 projects, and we started analyzing the questions. And we took the English questions to start with, so around 600,000 questions. And we basically had three main parts that we wanted to look at. First of all, similarity. So we wanted to say, just a simple question, how old are you, is similar with which year are you born, right? It's the same, you will get the same outcome of those questions. But they are completely different in terms of how you ask the questions. But the outcome or the question for a human is obvious, that is the same question. Then we want to look at correlation. So we said, but if you have asked question A, B, and C, then most likely you will also want to include question D, E, F, okay? And everything at the end of the day saying, yes, but we conduct research in 140 countries. We want to be able to have all this in at least 30, 40 languages validated, okay? So this has been the initiative. This is the focus of what we look at. On top of this, we started looking at the questions and said, well, a certain question is actually divided in different question blocks. So last 30 days, for instance, is a timestamp. That is something that can be last 7 days, last month, last whatever, okay? So we wanted to start stripping out the questions into the essence of the question. And I think, Anders, you will speak more about that. And of course, the main benefits is making sure that it's easier to create the questionnaires by pulling in questions and having a system helping you in this product. Easier global deployment of the questionnaires. And most of all, harmonizing the questions, but also making sure that we use the best wordings for a specific question. So that was extremely important for us. And then at the end of the day, also looking at which are the questions that should be presented to the client in which way. So that's the background. And then on top of everything, we also put a certain level of calibration from researchers, asking researchers to score and say, what is the score of this question? How similar is it? How well does it correlate? So a manual approach to it just to validate it that the system is doing the job. With that said, I would like to pass over to Anders, who will give you a much more and clear technical view of how he succeeded.
Thank you very much, Andrea, for that great introduction and actually keeping on time as well. I didn't think so. So I will focus a bit more on the technical aspects of how to build a similarity service. So specifically how to build it a bit more efficiently, and also how to take a model like Google BERT and adapt that model to the Ipsos domain for the market research use case. So let me just briefly go through some of the historical breakthroughs that we've seen throughout the years in NLP. And as many of you probably know, it's been around for a long time, since the 1950s. But there has been some transformative changes in just recent years. So in 2017, we had the huge self-attention model, the transformer, that broke state-of-the-art record for translation. And then we had in 2018, last year, Google BERT coming out that broke not one, but many different state-of-the-art records in NLP. And we can compare this a bit to what happened with images back in 2012. We could see the big AlexNet coming out. That also broke the record for image classification. And then the rapid succession of different deep learning methods to simply work with images in a very efficient way. So we can basically witness the same thing happening now, but for text. And what we can do now is actually to start to understand text in a much more semantic way than ever possible before. And to demonstrate that, here is a small prototype from Peltarion that is trained on QQP. It's a data set from Quora.com, which contains 400,000 questions. And if we ask that model a question like, will artificial intelligence end the world? We can see the most similar one being very similar. Will artificial intelligence really end the human race? But what is more interesting is if you look at the second to most similar question, that basically says, is technology destroying humanity? None of the words in that question is similar to the original query. And this is really what we want to have. So if we adapt this to the Ipsos domain, here are Google BERT trained on Ipsos data on the 600,000 questions. And we can ask the question like, what is your primary bank? And you see the most similar one being very close. But once again, the second to most similar says, and which of these is your main bank or financial institution? And once again, it's very few of the words that are in common, but the BERT model can still understand that the semantics is the same. And as we said before, BERT can do many different things. You can see a number of tasks here, and we at Peltarion have experimented with all of them. But for this specific use case, we are focusing on 3 of them. So one is simply the embedding extraction, taking a single question and getting some fixed size embedding for that. We also are going to use named entities, and of course, semantical textual similarity. So before I go more into how to build that, let me just quickly introduce Peltarion as well. So Peltarion is a company that's been around for 15 years. And it started off with the 2 founders that basically had a consultancy firm and always focused a bit on neural network technologies, long before they actually became popular. And then in 2016, people started to understand the importance of AI and all the amazing achievements and progress that has happened then. And we could see the big tech companies of the world, the Google, the Facebook, the Amazon, they knew how to make proper use of these techniques. But we could also see that most other companies failed when they tried to use this type of technology. So the investors came to Peltarion and asked, can you transform your company from being a consultancy firm to actually becoming a product company that builds tooling that allows any company to start making use of these techniques and do that in an affordable and easy-to-use way to truly operationalize AI? So that is what we have been doing since then. And we have grown from 2 people to 80+ people now in 3 years. And let me now move into the more interesting question. How can we build a service like this? So the first thing we need to have, of course, is to have the right data for building up a similarity service. So we can do this in 2 different ways. So BERT can be trained first with unlabeled data to build a language model. So Google has done that partly for us, training BERT on Wikipedia and 7,000 books. And then we can choose to fine-tune that further, just a language model using public data set or data directly provided by Ipsos. So we can make it understand the type of question and grammar that Ipsos make use of. Then we can choose to fine-tune the actual task itself, like the similarity task. And once again, we can choose to use some kind of public data set. Or in this case, we actually have labeled data from Ipsos directly that we can train on. And here you see some example of that data. So the actual process for training the model is to, for one, start with the pre-trained version, the green boxes you can see here that is provided by Google. And then the red one is what we can do at Peltarion to continue to fine-tune, for example, the language model or the actual task itself. And we can choose to use either public data sets like Microsoft's or directly using Ipsos data. And from that, we can extract embeddings from the full data set of questions and do similarity predictions, build an API, have some kind of web front end, which Ipsos then can integrate into their system, which they have done. So I'm not going to go too much into the technical details here, but I wanted to understand at least the differences between these two approaches. So one of them is trying to basically take one query that you want to send into that system and concatenate that with all the questions that we have in a data set, 600,000 of them. But that would take a huge time, like 10 minutes. So that's not really an acceptable time to do so. So instead, we can extract the embeddings in advance, and then we take the query, extract the embeddings, and do one single large matrix multiplication. We sort the answer, and then we get some similarities. And that can be done really, really fast and still is surprisingly efficient. So finally, let's talk a bit more about how to adapt to the actual Ipsos domain. And I spoke already about two different ways to do so. One is to tune the actual language model with unlabeled data. And we can also tune the task itself with labeled data, saying how similar, according to Ipsos researchers, two questions really are. But we still have a problem like this. So here is an example of a question which has a large number of very redundant questions. The only thing that really differs is the brand and the product. So this doesn't really result in a good user experience, and we want to reduce them and remove the redundant questions. So how do we do that? Well, we can take the full data set, and then we can annotate named entities. That is what Andrea showed before, these kind of speak parts that you can mark. And using that annotated data, you can train a second BERT model that learns to predict named entities. And that works surprisingly well. And with that trained model, we can then infer entities in the full data set, and then simply deduplicate those questions. And then we go from having 600,000 to what you see in the second bar, around 300,000 less redundant questions. But we can do more than that. So given these 300,000 questions, we can now try to predict similarities between all of them, basically building up a big similarity matrix, and from that build so-called connected component, a graph of connected component where each component contains very similar questions. So a second reduction can then be done using these components, and that results in around 170,000 of very much less redundant questions. Make sense? So here is an example. When we use the named entity reduced dataset, we can ask the question, and we then have like placeholders for different entities, and you can see it's no longer being repeated for different types of, in this case, products and timestamps. And in this one, I wanted to show or give some sense of understanding how many different things we can start to experiment with. The first decision we have to do is choose some model to use, for example, the cased or uncased BERT model. We can choose different ways to tune the language model, use the pre-train, then fine-tune again on, for example, some public dataset, or the Ipsos dataset that we have, or the named entity replaced dataset. And then we can choose to continue to fine-tune the actual task itself. Once again, with public datasets or the Ipsos or the named entity dataset. Then choose different type of parameters, different pooling, and so forth. So all of this results in more or less a combinatorial explosion in different type of experiments we can run. And then we need to compare them somehow. We need to have some kind of evaluation metrics, and one common technique to do for this type of ranking problems is to use NDCG. So it stands for Normalized Discounted Cumulative Gain. So we use that, but have slightly modified it for similarity purposes, so we can handle these kind of regression tasks, which similarity is. So you see that formula to the right. So how did it go? Well, we're going to publish a paper about that that goes more into the details and the exact results. But I'd like to share some initial insights that we had from the experiments we have run so far. And one of them is that the language model tuning seems to be really effective and results in significant better similarity scores. You can see that between E1 and E2. There are some challenges by doing the task fine-tuning and how to avoid overfitting, and we are thinking into different augmentation techniques to prevent that. And the third really important insight is that the named entity approach that we take to reduce redundancy seems to also give a significant boost, as you see in the last E4 bar. So with that, I'd like to conclude a bit with saying, for one, BERT seems surprisingly efficient at being able to understand semantics and similarities between questions. There are a number of ways we can choose to tune that model to make it more related or works better for Ipsos use case. Some challenges how to do that exactly, and named entities works really well. But in short, I think this is a great example of how we use AI to augment humans and working together, humans and machines, and in that way make the process for Ipsos much more efficient. That is the way to truly operationalize AI. With that, I thank you for your attention.